Hello, my name is Abul Fazil Karimi. I'm a PhD student at University of North Carolina at Chapel Hill. My advisor is Dr. Parasara Shirdar Dugirala. The topic of this talk is formalizing traffic rules for uncontrolled intersections. Let me start first by introducing the motivation behind our project. We chose to study intersections since most accidents happen at intersections. For example, 47% of accidents in the United States in 2015 happened at intersections. Also in California between the years 2014 and 2017, 89% of the accidents involving automated vehicles happened at intersections. Intersections are inherently prone to accidents since we have a resource sharing problem. For example, in the picture, the two left turn lanes share some intersection area. One measure to coordinate the traffic around sharing the road is the traffic rules requirement. Traditionally, the traffic rules were written by humans for humans. However, we now have a new type of drivers, which are automated vehicles. A set of traffic rules need to be comprehensible to all traffic agents so that each agent understands its own responsibility, also can predict other agents' behavior. However, the driving handbook written in natural language is not immediately accessible to automated driving software. One approach to address this is to translate the rules in natural language to a formal language that can be processed automatically by automated vehicle software. Therefore, we have a translation problem. Now suppose that we have a formal version of traffic rules. What can we do with it? One immediate application, as we motivated, is to use it in the automated vehicle software stack for planning, control, and prediction. Another application is for third parties who want to certify a given automated vehicle implementation. Due to the combinatorial explosion of scenarios that the vehicle must be tested for, we need an automated procedure that can determine whether the vehicle under test abided by or violated a traffic rule. So we can use the formal traffic rules for this purpose. However, possible applications are not limited to automated vehicles. We can use it for traditional traffic as well. For example, monitoring traffic for violations, similar to red light cameras. Also, it can be used in simulators to generate traffic that abide or violate some traffic rules, say for accident analysis. To demonstrate our approach for formalization of traffic rules, we chose a subset of California's traffic rules and developed a formal version of them. These rules concern the right-of-way at uncontrolled intersections. We integrated the rules in the Carla simulator's traffic generation so that the vehicles follow their right-of-way. In this video, you see several intersection geometries: a multi-lane four-way intersection, a three-way intersection, a perpendicular T-intersection, and a skewed T-intersection. The reason we chose uncontrolled intersections is that they are the most common type of intersections in the United States. Also, if the lights at the signalized intersection fail, say due to a power outage, then that intersection has to be treated as an uncontrolled intersection. Now let's consider the translation problem. We want a formal language that is computable. That is, given a traffic scenario, we should be able to compute the truth value of each sentence in the traffic rules. Also, the syntax and semantics of the language should be as simple and intuitive as possible. This will simplify the manual task of translation. Another challenge is that in a translation, especially from an informal language to a formal language, some meaning will be lost. And ideally, we want to minimize this loss. To give some context and contrast, let's look at two related previous work. The urban multi-lane spatial logic is a custom-made logic to prove safety of automated vehicle controllers. Here, safety refers to collision freedom, which is one of the requirements imposed in traffic rules. However, our goal is to formalize all traffic rules in the driver's handbook. For example, right-of-way rules concern fairness and efficiency of traffic flow and are not just about collision freedom. This logic is quite technical and not as intuitive and simple as first-order logic, which we will use. The logic is computable, however, we are not aware of its computational complexity. The next approach is close to our work, in which they translate traffic rules to a formal version. They use linear temporal logic to capture the logical form of the rule. In contrast, we used first-order logic. Note that predicates are common in natural language, and first-order logic enables us to model them more faithfully. In LTL, you have only access to propositional variables and cannot parameterize them with subjects and objects. Another difference from our work is that to handle the temporal aspect of a traffic scenario, we use predicates that represent discrete events. Events are not only a common concept in the traffic rules, but also in simulators and game engines. To elaborate a little more on LTL, consider this example when the ego vehicle wants to overtake the other vehicle on a highway. In this rule, the predicate change has object parameters fast lane and right lane. But in the formal version, this structure is not present. Instead, we just have a propositional variable merging. Therefore, we adopt first-order logic to formulate the rules. We interpret the formulas in a denotational way, which is a well-known and intuitive semantics. In particular, terms of the language may denote traffic objects. The objects may be physical, like vehicles and pedestrians, or conceptual, like a fork. Also, timestamps are treated as objects. That is, they interpret the time parameters of event predicates. Finally, predicates denote mathematical relations. Let's go through an example. Consider this rule. At intersections without stop or yield signs, yield to the vehicle or bicycle on your right if it reaches the intersection at the same time as you. First, notice that the phrase without stop or yield signs specifies the context of the rule, that is, in which circumstances the rule applies. We separate the context specifier and consider the rule itself. In this form, the rule has some implicit references. So first we make them explicit and dereference the pronouns. To make the subject explicit, we also change the tone of the language from imperative to assertive. This is a change of perspective from driving instructions to legal requirements. We get, if vehicles V1 and V2 are at the intersection, V1 arrived at the same time as V2, and V1 is on the right of V2, then V2 must yield to V1. Now it is straightforward to code this as a first-order formula. Note that in our yield predicate, we keep track of the reason for yielding using a third parameter, which is yield to right here. This is one way of bookkeeping this information. Alternatively, we could have had different yield predicates instead of a parameterized one. Now we need to define each predicate that appeared in the rule. If a predicate has enough logical content, we define it as a first-order formula based on simpler intuitive predicates. Otherwise, we treat it as an atomic predicate and give a mathematical definition. For example, vehicle V is at the intersection if it has arrived but has not entered the intersection yet. And vehicle V has arrived if it has arrived from some fork F at some time t. We treat the predicate arrived at fork at time as an atomic predicate, which represents a discrete event with t denoting its timestamp. Similarly, the predicate is on right of for vehicles is defined in terms of the arrival event predicate and also the is on right of predicate for forks. Atomic predicates that don't have a time parameter denote static facts. We have defined every predicate in the original rule in terms of atomic predicates. This completes the logical definition of the rule. Now we need to define the atomic predicates. Atomic predicates with a time parameter are defined as an event. For example, arrival at a fork is defined in terms of collision between the vehicle's volume with the fork's arrival box. A vehicle's volume could be any 3D mesh, for example a bounding box. Such an event can be efficiently computed using simulators' built-in collision detection. Similarly, each fork has an entrance box that generates the entrance event. In the picture, the blue box is the arrival box, the green box is the entrance box, and the green arrow shows the orientation of the fork, which is along its incoming lane direction. Each fork has one or more intersection lanes branching from it. For the is-on-write-off predicate for forks, we define it based on the angle between the orientation of the two forks. Imagine that the circle is the intersection area and forks approach it with different orientations. This completes our definition of the atomic predicates for the yield-to-right traffic rule. Now that we have completely defined a rule, we need to see how we interpret it for a particular traffic scenario. A traffic scenario specifies the geometry of the lanes and intersection, also the states and trajectories of the traffic agents. From the traffic scenario, we can compute all the events and static facts that are relevant to the traffic rule. An interpretation of the rules results in a model. A model includes all the logical conclusions of the rules. For example, whether a particular vehicle must yield to another in the given traffic scenario. This interpretation is a harebrained semantics since the denotations of the predicates in the rules are based on a set of ground atomic formulas, as provided by the events and static facts. By a ground formula, we mean a formula without variables. Consider the traffic scenario where two vehicles arrive at the intersection at the same time. The yellow vehicle arrives from a fork that is 90 degrees counterclockwise to the fork that the blue vehicle arrives from. Hence, the blue vehicle must yield to the yellow vehicle when both of them are at the intersection. Therefore, the yellow vehicle must enter the intersection first. In our implementation, the interpretation of the rule is done by a logic solver. The computation of the events and static facts are done using some manual code together with built-in functionality of the Unreal Engine. Here is a list of the rules that we modeled and implemented in this project. The first 4 rules are for generic uncontrolled intersections, while the last one is only for T intersections. One notable point is that Rule 5 is incompatible with Rule 3, since the traffic on the minor road can be on the right of the traffic on the through road. Hence, applicability of a rule to a context depends on the other rules for that context. Formalization of the rules is one step towards automatically checking the internal consistency of the rules. To give you a sense of what predicates are used and the level of their intuitiveness, we present a partial list here. Recall that auxiliary predicates are defined using the atomic predicates and logical connectives and quantifiers. Also, the only predicate that contains a time parameter but does not denote an event is the comparison between two timestamps. This comparison predicate simply denotes the comparison relation between two natural numbers. In summary, we provided a formal but intuitive translation of the traffic rules. Each informal rule corresponds to a single formal rule. This simple mapping facilitates auditing the formal version against the original natural language document. In our modeling, we made intuitive design choices to represent the traffic rules more faithfully. However, to test how much the formal version of the rules align with the informal natural language version, we need a ground truth for the intended meaning of the rules. For example, we could use a library of traffic scenarios that are labeled with legal obligations and violations of each traffic agent. One may look into whether there is enough data available from traffic authorities to form such a labeled database. Another direction is to extend the semantics of the rules. For example, we can use 3-valued logic to model indeterminate facts, say when a vehicle does not know who reached the intersection first. Also, we can use fuzzy logic to model levels of confidence, say how much we are sure that the vehicle reached the intersection later than the ego vehicle. As a very different direction, we could use the formal rules to generate traffic scenarios, say to enumerate those scenarios in which a vehicle violates a particular rule. Finally, I would like to give a few references that I used in this presentation. For accident statistics, see the first two references. The last two references are the previous work related to our project. Thank you, and I'll be happy to answer any questions.